Okay, question 4 is the tricky one. Why am I saying that this is tricky? Because the density is different and your volume is, I think it's different as well, right? Oh, wait a minute. Oh, okay, so it's the density that is different, volume is the same. So because of that, if you go and use D equals to M over V, you realize that your mass is different. So I suggest you quickly go and put here the mass. Okay, and then 2 sphere, 50 cm cube. So just calculate out first. So 8 times 50. Do you need to change to meter cube? No need, right? Because here cm cube, here also cm cube. So down here, this will become 400 gram. 2.8 times 50, 140 gram. And for the water, you have 100 cm cube. So you will get 100 gram. Okay, so the mass is different. Explain why the temperature of both spheres cannot be greater than 100. So you have to say, number one, they are in thermal equilibrium. I'm not going to copy out everything, okay, because I'm actually running out of time and because I need the time, yeah, to play game. So anyway, you are the one learning. I just need to teach you, right? Okay, yep. Justified. Okay, thermal equilibrium is the first point that you must mention. And of course, thermal equilibrium, if you just mention this alone, you are actually paraphrasing this line. So this alone will not give you the full credit. What makes a temperature constant is because there is no net, okay, transfer of heat, okay, at thermal equilibrium. And hence, there will be no temperature change and it won't go greater than 100. Yep. And of course, because water boils at 100, right? Unless you put it in hot vapor, then you can get more than 100. But I think because this is just 1 mark, you can leave it there. If it is 2 mark, then you need to elaborate a bit more because water boils at 100 at constant temperature. So if you put it in liquid water, it will be just 100, that is the max. Okay, but if you put it in vapor, then it can go above 100. Okay, this one, remember. Okay, now calculate the heat capacity of the sphere made up of X. So, heat capacity. Let me see. One megawatt suspended for 10 minutes. The sphere is transferred beaker A. Oh, okay. Actually, you don't need to read so much. Now, what is given here is the specific heat capacity is per kg. What they want is the heat capacity. So heat capacity, it is dependent on the mass. So what you need to do is very easy. You just need to play with the unit. So can you see here is joules per kg per degree C. So I will just write it here so that you can follow the trend. So I have joules per kg per degree C. This is specific heat capacity. Okay, you want to change it into heat capacity, which is joules per degree C. So what is the difference between this unit and this unit? The kg here, right? So what do? You multiply by kg. What is this? This is the mass, specific heat capacity, heat capacity. Heat capacity is with a big C. Yeah, so you just need to do that. So this one, okay, if you have confidence in your formula. Actually, this one is given in the formula list. So this one is specific heat capacity, small c, multiplied by the mass will give you the big C, heat capacity. So therefore, big C is here. X will be 380. The mass we have already calculated. Be careful, the one that we calculated is 400 gram. This one is in kg. So down here, you have to put 0.4 kg. Okay, and then you will get the answer. 380 times 0.4 kg, you will get 152 joules per degree Celsius. From your answer to B, explain why sphere B will cool down at a slower rate than spheres Y, and I have to give numeric value. So I have to use my answer in B. So since I'm comparing things, right, I may as well find out what is my heat capacity of Y. So heat capacity of Y, it will be just 700 times 0.14. I will get 98 joules per degree C. Now, why am I finding the heat capacity, and why am I using this to do a comparison here? The reason why is because the mass is different. Okay, so if I use the heat capacity, I do not need to consider like, oh, why this one different mass. Okay, if I use specific heat capacity, it is per unit kg, right? So if I use specific heat capacity, I need to make my mass a control variable. But if I go and use heat capacity, then my difference in mass is already taken into account. Okay, because I multiply by the mass of the subject that I want to test on. Okay, this question, if you have doubts, please approach me. Okay, so for now, so if you look at this, my specific heat capacity here is larger, my heat capacity here is lower. Okay, now I have to make one assumption, that is the rate of heat loss. Right, because this value only tell me that, oh, if X is supposed to drop by 1 degree C, X must give out 152 joules of energy. And if Y decrease 1 degree C, I have to give out 98 joules of energy. Yeah, so just by looking at this, well, you can say that, oh, okay, Y only need to lose 98 joules, it will decrease by 1 degree C. This one need to lose 152, so therefore X will not be cooled down as fast. But there's an assumption. The assumption is the rate of heat loss for X and Y must be the same. What do I mean by that? Now, if you assume X lose heat at 200 joules per second, okay, heat loss for X. But if my heat loss for Y is made up of wood, is something insulator, it loses heat very slowly, let's say 10 joules per second. Which one will cool down first? This one, right? Because within 1 second, it will already lose 200 joules, that means it will decrease by at least 1 degree Celsius. This one, after 1 second, it will not decrease by 1 degree C, because only lose 10 joules per second. So therefore, when you are explaining this kind of question, you have to make your assumption very clear. You are assuming, okay, X and Y has the same rate of heat loss. You must state your assumption. So therefore, since X has a higher heat capacity, bracket 152 joules per degree C, compared to Y's heat capacity. I'm writing this lengthy thing because it wants me to state the relevant numeric value. So this is 98 joules per degree C. So therefore, okay, X would cool down slower because it need to lose more energy, okay, to decrease 1 degree C. First stop. Can? Okay, calculate final temperature of beaker B. Now, beaker B is which beaker? Sphere X is transferred to beaker A, sphere Y is transferred to beaker B. Okay, good. Common mistake for this question is that they think that the water in B has an initial temperature of 100 degrees C and then it becomes 30 degrees C. Actually, it's wrong. So what happened is, in beaker B, you have water of 30 degrees C and you actually have your sphere Y, which is at 100 degrees C. This is before they come into contact. So what happened after they are put in together? Okay, eventually they will reach thermal equilibrium, right? They will become the same temperature. So the water will become temperature T, the sphere will become temperature T, but we do not know what is this value. Okay, so that is what we want to find out. So use your energy equation. So energy loss, okay, by sphere Y must be equals to the energy gain by the water. Yeah, so once you have that, okay, use your MC delta theta Do you need to use MC delta theta? Oh yeah, specific heat, right? So your delta theta here will be energy loss. So it will be 100 degrees C minus the final temperature, right? Down here will be the mass of water multiplied by the specific heat capacity of water. This is heat gain, so it will be T minus 30 degree. Okay, so the T is not necessarily always at the back. You must make sure that this difference is a positive value. Yeah, so once you have that, put in your values. So remember it's in kg, so this one is 0.14. This is 700. This is 100 minus T. This one is 0.14200 T minus 30. Okay, then you all solve the algebra yourself.